Hello and welcome to another lesson from Level Up Mathematics. In today's lesson, we will be exploring some key attributes and vocabulary surrounding functions. Now, graphs are one of the most powerful ways of visualizing a function's rule because you can easily see the key features or attributes of the function. When graphing a function rule, the graphical representation will either be discrete or continuous. So let's talk about the difference between discrete data and continuous data. So in discrete data, the data points are not connected. They are not connected. So if you have a little graph here, you're going to have a set of like individual little dots, okay? Discrete data is used for things that are being counted. The input variables are isolated, distinct, and domain and range are listed in set notation. For example, you could have something like 2, 3, 4, something like that. Okay, so an example of discrete data might be if you had a problem that talked about the number of tickets sold to a movie or the number of people in the 7th grade. I don't know, number of cookies that a recipe might make. So just things that are being counted will always be discrete, non-connected data. All right. Now, continuous data is connected data. The graph can be drawn without lifting your pencil. So you might have something like this, a continuous line, okay? It's used for things which are being measured. Domain and range will be listed using inequality notation. So like in the previous example, 2 is less than or equal to x is less than or equal to 4. So some examples of continuous data might be time or distance, things like that, okay? Now, in example 1, it says, excuse me, a set of weights includes a 4-pound barbell and 6 pairs of weight plates. Each pair of plates weighs 20 pounds. So let's kind of highlight what we know about our weights here. We have a 4-pound barbell. We have 6 pair of weight plates. Each pair of plates weighs 20 pounds. If X pair of plates are added to the barbell, the total weight of the barbell and plates in pounds can be represented by the function rule f of x equals 20x plus 4. Represent this function as a table and a graph. So let's start with our table here. So number of pairs of plates. Now, when you have a barbell, you could have 0 pair of plates on that barbell. And in this situation, that barbell weighed 4 pounds. Okay. What if I put on 1 pair of plates? That would be a total of 24 pounds because we do 20 times 1 plus 4, right? For 2 plates, that would be 20 times 2, which is 40, and 40 plus 4 is 44. For 3 pair of plates, 20 times 3 is 60, and 60 plus 4 is 64. Hopefully you can see the pattern here now. So 4, 5, 6, so this would be 84, 104, 124. Now, to make a sketch of this, if we have 0 plates, we had a total weight of 4 pounds. So I'll put like a dot about right there. 1 plate would be a weight of about 24 pounds. 2 plates, 44 pounds. 3 plates, 64. 4 plates, 84. 5 plates, 104, 6 plates, 124. So I'll go off the grid just a little bit. Now, let's talk about whether we should connect those dots. So, because our pairs of plates are being counted, you can't put on 2.5 pairs of plates. You put on 0 plates, 1 pair, 2 pair, 3 pair, 4 pair. That means this data is discrete, which means it's not connected. So do not connect discrete data points. Okay. Now, because this is discrete data, we have to write our domain and range in set notation. So in set notation, this would just be 0, 1, 2, 3, ... to 6. The x values. Remember, domain are the x values of your function. Now, the range are your y values of the function. We're going to also list it in set notation. So 4, 24, 44, 64, 84, 104, and 124. All right, example 2. A student rode his bike home from the rec center at a steady rate. When he left the rec center, he was 9 miles from home. He arrived home after 28 minutes. Represent this situation with a graph. So to represent it with a graph, let's represent it with a table first. So let's let the x-axis be our number of minutes, and we'll let the y-axis be the distance from home. So when he left the rec center, so at time 0, it said he was 9 miles away from home. And then he arrived at home after 28 minutes. So when the minutes were 28, his distance from home was 0 miles. So now we've got 2 points that we can plot. So 0, 9 would be right here, and 28, 0 would be right here. Now let's talk about whether or not we should connect these 2 dots. So let's talk about our domain, our number of minutes. All right. Now minutes, we can, when we're dealing with time, we can have fractional amounts of time. Like I could say that he was riding his bike for 1.25 minutes. That means this data is continuous data. Okay. Time is continuous. All right. So we will circle continuous right here. Now, when we write domain and range for continuous data, we must use inequality, compound inequality. So remember, our domain is the set of all x's, and our range is the set of all y's. So let's label our beginning point 0, 9 and our ending point 28, 0. And remember, for the domain, when you're writing a compound inequality, you look at only your x values. So I'm going for 0 to 28 minutes. I'll put an x in the middle, less than or equal to, less than or equal to. So what this means is x is greater than or equal to 0 and less than or equal to 28 minutes. So the time of this function was greater than 0 minutes, but less than or equal to 28 minutes. Now the range of this function is the distance from the rec center. The distance from the rec center. So for range, we'll be looking at the y values. Now when you're looking at range, you want to go from the bottom of the graph, which is 0, to the top, which is 9. So 0, 9, y, less than or equal to, less than or equal to. So what this is saying is the distance from the rec center must be greater than or equal to 0, but less than or equal to 9. All right, when analyzing the graph of a function, it's often helpful to describe special points on the graph, such as the graph's intercepts, maximums, minimums, and zeros. Now, some of the vocabulary we're going to look at, you will have heard from previous courses, and some of the vocabulary may be new. So we'll talk about the vocabulary of these functions as we move through the examples. So in example 3, it says identify the intercepts, the zeros, the domain, and the range. So in our first graph, we have a linear function, and it wants to know if it's continuous or discrete. Well, since the line is connected, we're going to say that it is continuous. All right. For the x-intercept, well, the x-intercept is where that line crosses the x. So let me put a label here on the x-axis. So where does that line touch the x-axis? Well, it touches it right here, x-intercept. So I'm going to label that, and I want you to label your graph so you can start getting used to this terminology. You've probably seen this term in previous courses. Now, the x-intercept here we'll write as an ordered pair would be 2, 0. Now, while we're talking about x-intercept, the x-intercept of a function also has another name. So I'm going to put that other name. The x-intercept is often referred to as the zero of the function. So the zero of this function is x is equal to 2. So really the only difference is that on an intercept, I write it as an ordered pair, 2, 0. And for the 0, I just simply write the zero of the function is x equals 2. Now, the y-intercept is where that linear function, that line, touches the y-axis. So this particular line touches right here, and let's label that. So label your graph for me, please. Y-intercept. And so that would be the ordered pair 0, positive 4. Okay. Now, to get the domain, you want to look at the right side of the graph and the left side of the graph. So on the left side of the graph, it's going to the left forever. So that would be negative infinity. On the right side of the graph, it's going to positive infinity. Okay, so negative infinity to positive infinity. We have a shortcut that we can use when we have negative infinity, positive infinity, which is all real numbers. Now, for the range, we look at the bottom of the graph. Now, the bottom of this graph is going downward to negative infinity, and the top of the graph is going upwards to positive infinity. So again, I'm going to have the same situation here, but I'm going to use a y in between them. So the range is also all real numbers. Box in our final answer, okay? That is the shortcut way of writing negative infinity to positive infinity. All right, so for our next function here, we have a U-shaped graph that opens up, and it wants to know if it's continuous or discrete. Well, since it's all connected, we would say it's a continuous graph. Now, in this problem, something interesting happens because when they're asking us for the x-intercept, there are actually 2 of them. So look at the graph and see if you can figure out where does that U-shape touch the x-axis. Where does that U-shape touch the x-axis? And put a dot there for me, okay? And label that x-intercept, x-intercept. While you're at it, also label it 0. Okay, so the x-intercepts are negative 2, 0, and positive 2, 0. The zeros are x equals negative 2 and x equals positive 2. So we got 2 answers there right off the bat. All right, the y-intercept is asking where does that U-shape touch the y-axis? Well, hopefully you can see it touches it right here. So would you label that for me, y-intercept? All right, now y-intercept we write as an ordered pair, so 0, negative 4. All right, for domain, this is our set of x values. So it's going to the left to negative infinity, and on the right, it's going to positive infinity. So again, this is our long way of writing the domain, but we will use our shortcut, all real numbers, as our final answer. All right, for the range, The range is the bottom of the graph. So the bottom of this graph occurs at -4, and the top of the graph occurs at positive infinity. So it's going from -4 at the bottom all the way up to positive infinity at the top. So we would write this -4 less than or equal to y less than or equal to infinity. But then the shortcut way of writing that would be y greater than or equal to -4. We're just using this part of the compound inequality to write our final answer. So y is greater than or equal to -4. All right, in our last set of data, the data is not connected. So data that is not connected is considered discrete data. It has an x-intercept. Let's label it. Let's label this point as x-intercept and 0. So for x-intercept, we would put -6, 0, and the 0 of the function is -6. X equals -6. Okay. For the y-intercept, it touches the y-axis right here at 0, 4. Now, to get the domain and range, it might be helpful for you to label these ordered pairs. So this would be -6, 0. This would be -3, 2. This would be 0, 4, 3, 6, and 6, 8. All right. The reason I say it's probably easier to label these is because we want our domain, we want these x values, okay? Because this is discrete data, we will list it in set notation. So -6, -3, 0, 3, and 6 for the domain. For the range, we want our y values. So 0, 2, 4, 6, and 8. 0, 2, 4, 6, and 8. All right, example 4. The graph below shows a function f of x. Use the function to answer the questions. So some of this will be review from previous lessons. For example, in problem A, it's asking us to evaluate the function for f of -4, f of 6, and f of 0. So remember, these are your x values. So what this is saying, if you go left 4, how many will you go up or down to reach that function? If you go left 4, how many will you go up or down to reach the function? So let's try that. 1, 2, 3, 4. And notice we're going to have to go up. 1, 2, 3, 4, 5, 6. So we went up 6, so positive 6. Okay. All right, next one. F of 6. That means if you go right 6, how many will you have to go up or down to hit the function? So 1, 2, 3, 4, 5, 6. Notice you'll have to go down 1. So that would be -1. All right, last one, f of 0. So we're not going right or left at all. So put your pencil at 0 and then go up 2. We would land right there. So we're going up 2 to land on the function. All right, now the x-intercepts of the function. Let's see where this function touches the x-axis. So it's touching it right here. Let's label that. And we'll go ahead and label it as a 0, 2. And it touches right here, too. So the x-intercept, 1, 2, 3, 4, 5. So -6, 0. And the other x-intercept, 1, 2, 3, 4, 0. So there are 2 of them. All right. Now, once we know our x-intercepts, we can answer part D. What are the zeros of the function? X equals -6. X equals 4. All right. Part C. What is the y-intercept of the function? Where does the function touch the y-axis? So here is our y-intercept, if you want to label that. That touches the y-axis at 0, 2. All All right, the function has a maximum value of blank at x equals blank. So that is the top y value. A maximum is the top y value. So look at the graph. You want to find the highest y value on that function, and it occurs right here. So let me label that as maximum. And we'll label that point is at 2, 1, 2, 3, 4, 5, 6, 7. It's at 2, 8. So it has a maximum value of 8 at x equals 2. It has a maximum value of 8 at x equals 2. Now the minimum of the function is the lowest y. So that occurs right here. And that would be at the point 1, 2, 3, 4, 5, 6, 7, negative 8, 1, 2, 3, 4, negative 4. So our lowest y value is negative 4, and that occurs when x is negative 8. That's our minimum value. So for the domain of the function, we want to go left to right. Left to right. So here is our point on the left. So we're going to need that point. We want the x value of that point. And then we need the point that's all the way on the right. That would be right over here. Let's see. So let's label that point 1, 2, 3, 4, 5, 6, negative 1. So that on the left, we're going from negative 8, and we're going all the way over on the right to x equals 6. So our domain would be negative 8 less than or equal to x less than or equal to 6. Now for the range, we want the lowest point on the function, which occurred right here at negative 4, and the top point of the function, which occurred right here at positive 8. So our range would be negative 4 less than or equal to y less than or equal to 8. It looks kind of messy. Let me rewrite it. All right, and that concludes today's lesson, Attributes of Functions.